Alright, hello again everybody. So in this video we're going to apply our big O analysis tools to a sort of like, classic computer science problem, which is called the maximal contiguous subsequence sum problem, which is usually abbreviated as MCSS because, ain't nobody got time to say that over and over. So the idea of this is we're given a sequence, like a vector or something like that, right? We want to find the largest sum that can be formed from any contiguous subsequence. Since that's kind of vague, let's break it down a little bit here. So what's a contiguous subsequence? That's just a portion of the sequence with no gaps in it, right? So like you're going to start at some position I, you're going to end at some position j, which comes after I, and you have to include everything between I and j. You're not allowed to skip anything there. Now, one thing to note is you are allowed to have an empty subsequence, a subsequence with nothing in it there. That is a valid contiguous subsequence, so that'll sort of be important later on there. Once we have a contiguous subsequence, you can form the contiguous subsequence sum, which is just, add up all the stuff in your particular subsequence there. If you have an empty subsequence, you add it up and you say that the sum is 0 there, like that. So that's sort of like the sum of that there. So then the problem we have, the maximal contiguous subsequence sum problem, is out of all the possible contiguous subsequences, so all the subsequences that you could make, what is the largest sum that you can find? Now, since we could pick the empty subsequence, which sums to 0, right? That is one of our options. The maximal contiguous subsequence sum can never be negative, right? Like even if all the numbers in your sequence are negative numbers, you could always just say, well, I'm going to take the empty subsequence that sums to 0, and 0 is bigger than any negative number there. We don't have to worry about the sort of maximal contiguous subsequence sum being a negative number. It will sort of like, it bottoms out at 0 basically. So in terms of code, this is going to be a function that takes a vector of ints as its parameter. It doesn't have to be ints, could be floats as well here, but we'll do it as ints just for sake. And it returns the maximal sum, just a single int there like that. We're not really interested in like which subsequence gives us the maximum. We just want to know what is the maximum, what is the max sum there. All right, so that's what we're trying to do here. Okay, so let's say that we're given this sequence here, right? So this is our vector right here, v or something like that, whatever we're calling it. And we want to figure out what is its maximal contiguous subsequence sum here. So we could just start somewhere here. So let's just say that we're going from 1 to 4. So that would mean I is at 1 and j is at index 4 there. So if you add up the stuff in there, -3 plus 3, of course, that's 0, right? And then -1 plus 5 just gives me a sum of 4, like that. Now, if you look at this, right, we can improve it pretty easily in a couple of ways here. So the first obvious easy thing we can do is we can drop the -3. Like all that is doing is hurting us. So if we drop the -3 and just start at 2 to 4, so I is there, right, and j is there, then we get 3 minus 1 is 2 plus 5, that gives us a sum of 7 for that. In a similar vein, if we extend our sum to include this 2 over here, right, so now we're starting here and we're ending over there, then that will help us out, right? So that'll be the 7 that we had before, plus 2 gives us a sum of 9, like that. That's pretty, so those two are pretty obvious, right? If you start with a negative number, throw it away, it's only hurting you, right? If we had a negative number at the end, we could chop it off and that would help us. If you have a positive number at the beginning that you're not including, add it. If you have a positive number at the end that you're not including, add it. But there's still one more improvement that we can do, and this is why this problem is sort of interesting. If we look over here at these two, right? So we were looking at starting here and ending there. If I just add this -2 here, that would hurt me, right? But it's worth it to push through the -2 to get to the 3 on the other side, because 3 is bigger in magnitude than -2 there. So that's what makes this sort of interesting is sometimes you have to push through a negative number to get to a positive number on the other side of it there. Like if we look at the beginning of this sequence here, right, we dropped this -3, but instead of there was a 2 here, imagine there was like a 7 there, right? Then it would have been worth it to push through the -3 to get to the 7 on the other side of it there. And in fact, like the 3 over here that we're trying to get to, that doesn't literally have to be a 3. Instead of being a 3, that could have been a 1, a 1, and a 1, right? Like 3 separate values. And if we have this, none of these are sort of bigger than the -2, right? Like none of these are obviously like more valuable than the -2, but their sum together works out being worth it to push through the -2 to sort of get to there. So that's what makes this kind of interesting. Like it's not obvious of just like, oh, when do I start, when do I stop here? Sometimes you have to push through negative numbers to get to sort of more valuable positive numbers on the other side there. Okay, so our first attempt here is, when programming, a lot of times where you start is just like do the dumbest thing possible and see if it works. So we're just going to brute force it. We're just going to search all possible contiguous subsequences and keep track of what's the sort of biggest sum that we've seen so far there. And that'll end up being kind of slow. So then our second attempt, we'll sort of notice that we're like repeating some work and we'll sort of eliminate that. And then that will improve our big O. And then our last one, we will sort of dramatically overhaul the way that we're approaching things here and make it so that we can do it in just one loop over the whole sequence there. But first, let's just start by doing like the dumb thing. We'll just check all possible subsequences. So we're looking for all of the sort of starting and ending points, all of the I and j here that are between the starting and ending points of the whole sequence there. So greater than or equal to 0 and less than n, the size of the sequence there. Now, this little sort of like, technically bit in here is we don't really care about sequences that like end before they begin, right? So we don't care about sequences where I is earlier than j. So we could fix things so that j is always greater than or equal to I there. That'll make the analysis, like the big O analysis, a little bit more tricky if we do that. So I'm not going to do that with like the first version here. I will sort of show you the code for doing that, but like I'm not going to do the analysis based on that. It just makes like the big O a little bit more mathematically sort of fiddly there. So then once we've picked out like, okay, we're going to start here and we're going to end here, then we're going to do another loop to sum up all the values between those two positions here. So that leads to a loop inside of a loop inside of a loop. We have a loop to pick I, a loop to pick j, and then inside of both of those, a loop to sum up all the stuff between I and j there. So that looks like this. This is my MCSS function here, right? I'm taking my vector as a const reference for the reasons that we've sort of talked about before, and we're returning an int here. So m is the biggest sum that I've seen so far, and then I have my I loop is picking the starting point, and then inside of that my j loop is picking the ending point, and then for each pair of I and j I'm going to do all of this stuff in here. So in here I'm adding up everything between I and j. This if in here is how I'm ignoring stuff that is like, outside of I and j, and also like ignoring backwards subsequences where j is less than I there like that. And again, like, it would be faster if we sort of didn't do that, if instead we said, okay, k starts at I and k is less than or equal to j like that. But that makes the analysis like now the inner loop depends on both outer loops. So the big O analysis becomes like a lot more sort of like mathematically tricky. I'm not doing that right here. I'm just using this if in here to kind of eliminate stuff that is sort of out of range here. So S is like our running sum of like what's all the stuff between I and j added up. And then down here we just check to see is S bigger than the biggest thing we've seen so far. If so, S becomes the new biggest thing. And when we're done, we just return the final sum there. So my K loop, that runs in O of n time, like that, right? It's just like a pretty simple O of 1 stuff inside it, and it runs n times. And then we wrap that up in the j loop, which also runs n times. So that's n squared. And then we wrap that up in the I loop, which runs another n times. So the total for the whole thing is big O of n cubed there, like that. That's not great, but we'll see later on just exactly how not great it is here. But obviously we would prefer something that's like in n squared or n territory if we can get there. But if n cubed was the best we could do, then that would just have to be what we would work with there. An improved version of this looks like this. So the outer loop is still the same here, like that. But now my j loop starts at I instead of starting at 0. And then instead of having that if inside of the inner loop, my k loop starts at I and goes less than or equal to j there, like that. So that's going to be faster, but now you can see that the big O analysis is going to be a lot more gnarly. Like this inner loop here depends on both I and j. And then the j loop also depends on I, where I is there, like that. You have to do that same kind of summation thing that we did sort of in the video about the big O examples there, only it's even more involved here because you need to consider I and j and k and sort of what pattern they have there, like that. This still ends up being O of n cubed. It's something like n cubed over 3 or something like that in terms of what the actual sum works out to. But in big O terms, it's still O of n cubed there. So that optimization doesn't change the overall big O of this here. So that's our sort of first attempt there. Okay, so we want to see if we can improve this here. So let's say that we have already sort of summed up the values between index 2 and index 4. So I is at index 2, j is at index 4. And we're just about ready to increment j to move it on to index 5. Now, normally when we do that, when we would increment j, then we would restart the sum and add up all the values from I up to the sort of new j there, like that. So we would start over at 3 plus -1 plus 5 plus 2 there, like that. But we already have the sum of 3, -1, and 5. We know that that is 7. So to increment j, to move it to 5, I don't have to throw away the work that I've just done. I can just add in the new element, the 2 there. So I just take the 7 that I already had, and then to move j to the next step, instead of restarting my sum from 0, I'm just going to add in the next term of the sequence. So that's basically going to let me eliminate the inner loop, the k loop out of it here, and move the summation into the j loop there. So I'll be eliminating one of those loops, and that will leave me in O of n squared territory. So that will look like this. We still have our biggest thing that we've seen so far. Our I loop runs from 0 to size, which we'll call n here, like that. But all of the sort of mechanisms for doing the running sum have got kind of moved out one level. So S is our running sum. We initialize that to 0. J starts at I. So I'm doing that optimization where I'm not even considering backward subsequences here. J starts at I and goes up to V size. We add in the next jth element into S, and then we test to see if that is bigger than the sort of old max we've seen here. So the only time we reset S to 0 is when I changes. Right? When I is incremented, that's when we reset S back to 0. That's when we sort of restart our sum there. In big O terms, this works out to O of n squared. This is like that sum that we saw earlier. So this is actually big O of n plus 1 over 2. But of course, when you simplify that all down using the big O rules, that just ends up being big O of n squared there, like that. So n squared, that's an improvement over n cubed there, like that. Again, like at the end, I've got some actual timing data. We'll see exactly how much of an improvement that is. N squared is better, but if we could get to O of n, that would be nice. So let's see about that. So again, like let's assume that we've sort of like we're summing some stuff up here. So let's say that I is here at 0 and j is over here at index 4. So we've summed up all the values in between there like that. So here we're going to observe that these first two values, 2 and -3, right? Those are just hurting us because they sum to -1. So this is called a prefix here. A prefix is just like, a part of the sort of subsequence that we're looking at that is at the beginning here. So this prefix of 2, -3, that's hurting us because its sum is a negative value. So if we chop that off and sort of restart our sum from not 0, but here, right? Then we'll get a better sum. We'll get a sum that sort of starts out better. So the idea is whenever we see a negative prefix, like a negative sum, we can quote unquote remove it. We're not going to like literally remove it, but we're going to reset our summation back to 0, sort of pretending like we're removing it there. So we're basically just going to loop through, and whenever we have a positive sum, we'll just keep going. But if we have a negative sum, we'll reset back to 0. So we start by building our running sum s, and s is initialized to 0, right? For each one, we're just going to add it into s. So we're going to do s plus equals the subscript I, like that. If the new one is bigger, we update m. So that's our if s bigger than m equals s, that right there. But if s is negative, then we're going to chop off the section before that. That means we're looking at a negative prefix here, so we're going to cut it off. So we're going to say something like, if s is less than 0, restart by resetting s equal to 0 there, like that. Sort of cut off that negative prefix that we just saw and pretend like the sum is starting over at the current position here. That leads us to this. So again, I've sort of folded the inner loop outwards here. So my s is now moved out to sort of like outside of any of the loops here. So we're going to loop over the elements here. Only one loop, right? Start at 0, go up to size. Add each new element that we see to s. If it's bigger than m, then we update m. That means we have a new max. Otherwise, if it's less than 0, then we reset and we remove that negative prefix there like that. So actually, you know what? Let me do this here. Let me scroll back, attempt to this thing here and clean this up. Let's go through this with this subsequence here. I don't have a sort of slide prepped for this, but that's okay. We should be able to make it happen, right? Okay, so let's do this here, right? Have to ignore the extra stuff here. So we're going to keep track of what is s and what is m. Right, so s is 0 and m is 0 initially. So we start by like we're here, right? We're starting at sort of this position here. So we're going to add the 2 into s. So now s is 2. And then we say, is 2 bigger than 0? Yes, it is. 2 is bigger than 0. So now 2 is my new biggest sum. Then we move on to the next one here, right? -3. We add the -3 into s. So -3 plus 2 gives me -1. Is -1 bigger than 2? No, it is not. Is -1 less than 0? Yes, it is. So then I'm going to chop that section off by resetting s to 0. So what that reset basically does is say, you know what, this part here is not going to help me. That adds up to a negative value. So I'm going to pretend as if the whole sequence started right there. So then we grab the 3. Now we're looking at this, right? We grab the 3, we add that to s. That's there. Is 3 bigger than 2? Yes, it is. So now 3 is a bigger sum than the 2 that we had before. Then we move on to here. So we add the -1 to s. That makes s go down to 2. Is 2 bigger than 3? No, it is not. Is 2 negative? No, it is not. So since s is still positive, that means it's worthwhile to push through this -1 to get to the stuff on the other side. Right? That -1 is not bad enough to cancel out the 3 that came before it there. So we're going to move on and see if maybe there's like some stuff on the other side of this -1 that we want here. And it turns out there is. So we have this 5. We're going to add that 5 to our 2. That gives us 7. Is 7 bigger than 3? Yep, yes it is. So now my biggest sum is 7. That's this sum right here, right? Then we're going to move on to the next one here. So now we're down over here. We're going to add that 2 to S. Oops. That 2 plus 7 is 9. Is 9 bigger than 7? Yes, yes it is. So now the biggest thing that we've seen is 9. So now our max sum is this sum right there, right? From there to there, from here to over there. Then we move on to the next one. So -2. -2 plus 9 takes me back down to 7. Is 7 bigger than 9? No, it is not, so I don't have anything better than there. But 7 is also not negative, so it is worth it so far to push through this -2 to get to the stuff on the other side of it. The -2, instead of looking at it the way we talked about it before, where it's like, okay, -2, it's worth it to push to it to get to the 3, now we're looking at it as, is the -2 sort of bad enough to cancel out all the stuff that came before it there? And it's not, right? Like the -2 isn't bad enough to sort of cancel out the 9 things that I had accumulated before there. All right, so then we're going to move on to 3. So we add the 3 to the 7. That gives me 10. Is 10 bigger than 9? Yes, it is. We update M to 10. So now my new biggest sum is all of that. Then we get -3. -3 plus 10 takes me back down to 7. Is 7 bigger than 10? No, it's not. Is 7 less than 0? No, it's not. So again, it's worth it to push through this -3 to get to the thing on the other side, if that sort of helps me out and makes things bigger here. And then finally, we move on to the last element here, which is the 1. 7 plus 1 is 8. Is 8 bigger than 10? No, it is not. We don't change our M. Is 8 less than 0? No, it is not. So we don't sort of chop anything off there like that. So when we're done, our final maximal contiguous subsequent sum is 10, and that came from this section right there. And notice that I just did one loop all the way through, right? At no point did I have to backtrack or sort of, go over this numbers that I've already been more than once here. So it's just one straight loop all the way from beginning to end. If we'd if I'd worked through the n squared version by hand here, we would have been like sitting here for an hour or something like that. So that's how the sort of better version kind of works there like that. So I did some timing of the sort of 4 versions that we looked at: our original cubic version, and then the sort of improved cubic version, and then the n squared version, and then the n version here. And the way that I sort of set these up was I tried to pick sizes for the vector so that I would end up with about 1/10 of a second, about 1 second, and about 5 seconds. Like I tried to find sizes for the vector that would give me those sort of like 3 sort of time intervals here. So for our original cubic version here, we can process 300 elements in 1/10 of a second. We can process 700 elements in 1 second, and we can process 1,200 elements in 5 seconds here, right? 5 seconds is about like the longest that I'm willing to wait for, an example program to run here. So like that's kind of where I sort of capped out there like that. So, the original version here, we can sort of practically use it on vectors up to 1,200 elements. Our improved version, right, kind of like, almost sort of doubles things here, right? So now in 1/10 of a second, I can do 600 things. In 1 second, I can do 1,200 things. And in 5 seconds, I can do about 2,100 things here. So these numbers are approximately, right, 2x of the original sort of cubic version that we had up above there like that. So they're a constant multiple of that, but it's still cubic. It's still sort of increasing like sort of cubically there like that, right? So this one sort of maxes out at about 2,000-ish elements. Like that's the max we can handle before I sort of get bored watching my CPU meter like max out at 100 or whatever there. For our squared version here, in a tenth of a second, like we're already seeing a big improvement. We can do 6,000 elements. Like our vector can have size 6,000, and that runs in a tenth of a second. In 1 second, we can process 20,000 elements, like 10 times what the improved cubic version can do in a fifth of the time there, like that. And then in 5 seconds, we can do 45,000 things there, like that. So that's better, right? But again, we're sort of maxing out at like 45,000. You have to wait 5 seconds to get your answer. Like that's kind of where I get sort of bored here, like that. Of course, you could, you can sort of look down here and see like the very bottom. The linear version just completely blows those out of the water. In a tenth of a second, our linear version is already more than 1 million elements here. In 1 second, we're 18 million. In 5 seconds, we're 900 million here. And if you plot these out, these have a nice linear relationship. So to go from a tenth of a second to 1 second, that's about a 10x increase in sort of like your runtime. This is approximately-ish like a little bit more than a 10x increase in size there, like that. Just for funsies, I went ahead and plotted these out over here and made some sort of nice bar charts here. So both of the cubic versions, this is the original cubic version in black, and then this is the cubic version that we improved in red there, like that. I plotted those together because they're both sort of cubic curves there, like that. Then the quadratic one is in blue, and the linear one is in green there, like that. I can't plot all of those on like the exact same chart because the scales are so dramatically different, right? This one maxes out at 2,000, this one at 30,000, and this one at like, I don't even have room to print the number on the chart here. It's, 900,000 is where that one sort of bottoms out there, like that. That's sort of like an illustration of how dramatically better the linear version is than either n squared or n cubed there, like that. And all it took was a little bit of sort of like poking at our problem and sort of looking at the shape of it to come up with the improved version of it there, like that. Now, to sort of finish things off here, I'll sort of like mention of something that's interesting to think about is if instead of doing the sum, what if we wanted the maximal sort of product here? How would that change the problem? Like, if you sort of think about it, right, like now we want to avoid zeros completely, right? Like a zero is like the worst thing that we could have because that cancels out everything that we've done. 0 times anything takes me all the way back down to 0. But negative numbers are not necessarily bad because if I can pair a negative number with another negative number, a negative times a negative is positive, and then it will help me. So it's a little bit more sort of interesting here. If you Google this, there's an easy sort of O of n algorithm that theoretically works, but there's a problem when you try to actually code it. When you're adding up ints, like the numbers stay sort of manageable, right? Like if you're just adding up a bunch of ints here, like things are kind of reasonable here. But when you're multiplying, the numbers get big really, really fast. They quickly become too big for an int, or even too big for a long. So then the problem comes not from like, okay, what's the algorithm? The problem comes from, okay, how do I keep track of the biggest thing that I've seen when I can't actually track what I've seen? Like I can't actually store the numbers, the products that I'm working with, but I still want to keep track of somehow of like, what's my running product? What's the biggest thing that I'm sort of looking at there, like that. So that's a sort of like moves the stuff in a different direction of how do we represent numbers instead of just like, oh, how do we solve this particular problem? So if you want, you could take a stab at that and sort of think about how to solve that there. The theoretical answer is this runs in O of n, but I think if you sort of introduce the stuff to handle the bigger numbers, that would change the big O of it there. So I'm not sure if there's a way to do this in O of n that actually takes into account the fact that like, hey, the numbers are going to get really big. You're not actually able to like represent the products in there. But anyway, hopefully that was an interesting example of applying like sort of big O to an actual problem. So we'll do this kind of stuff as we look at other algorithms. We say, hey, is there a better way that we can solve this? If we didn't have like the sort of, the tool of big O, right, we could still sort of see that like one of these functions is slower than the other there, but we wouldn't have a way to sort of like describe it without just running the code, right? We wouldn't have a way to sort of quantify exactly how much faster the O of n is than the O of n cubed, or how the increase in the size of the vector will affect the runtime of the algorithm. So that'll do it for this here. So next time we will take a look at a related sort of thing called amortized analysis, which is what happens if you run like the same function over and over and over there. Does it always sort of just add up, or does something more interesting happen sometime? But that'll do it for right now. Thanks a lot for your time.